this is part 2 of problem solving session. And in this part, we will remember how to use direct comparison test and limit comparison test to test the integrals for convergence. Okay, before dealing with the next example in which we will be using direct comparison test, let me remind you the statement of it. Direct comparison test. Okay, let's assume that we have functions satisfying these inequalities. For the first part of it, let's say we have this information about the convergence divergence behavior of the function g. Let's say we know that this is convergent. Then, depending on what you know, you can comment on whether this improper integral is convergent or divergent. Look at this inequality, please. Here it is given that the values of g of x are bigger than the values of f of x. And here, the given information tells you something more. The improper integral of g of x function, gx function, which has bigger values, is already finite. Then the integral of the f of x, which has smaller values, should be also finite too, right? If this is convergent, then this is also convergent. This is the first part of the statement, okay? So if g of x, which has bigger values, the improper integral of it is convergent, meaning that has a finite value, then this implies that the improper integral with the function having smaller values will also be finite, will also be convergent. Second part of the statement is like this. If you know that, now we have an information about the function which is smaller. If you know that the function with the smaller values, the improper integral of it is infinite, is divergent, then this information implies that the improper integral of the function with the bigger values should be already infinite. So this should be also divergent. So this is the summary of the statement of direct comparison test. Let me show you how to use it. For example, in the following exercise. So the question is, determine whether the given improper integral is convergent or divergent. So we don't want to find the result, the exact result of the integral. We just want to understand whether it is finite or infinite without giving the exact result. So here we will be using direct comparison test. We need to compare ln function with some other function so that we can invent some inequalities like that. So let me remind you some favorite graphs. So this is the graph of ln x function, and this is a line, which is the famous line y equals x. And as you know, the e to the power x function is the symmetric graph of ln x function with respect to this line. Okay, so after reminding these graphs to you, then you can see that ln x function is always less than y equals x function. Look at the given example. We need to deal with 1 over ln x, so take the reciprocal of both sides. If you reverse the functions like that, you need to reverse the inequality too. You cannot keep the same inequality anymore. Now, if I can find the behavior of this function, then I can comment on the convergence divergence behavior on the bigger function, right? Let's try to see. Here we will use p-test. Let me also put a recall about that for you. Recall p-test. P-test for improper integrals. We already covered what is the behavior of this, what kind of behavior this improper integral has, depending on p. So of course, it depends on the power p there. If p is greater than 1, something happens. If p is less than or equal to 1, something happens. If p is greater than 1, this improper integral is convergent and it converges to this particular value, this exact value. If this is the case, where p less than or equal to 1, we say that improper integral is divergent. We proved this result in our lecture notes. Okay, now we can use it directly. Turn back to our example. Here, what is p? What is the power of the denominator? Obviously, p is 1, so we are in this case, right? So the given improper integral is divergent. It is divergent by using which test? By using this test here, p-test. So now I will use direct comparison test to give the result. The function with the smaller values is already divergent. We obtain this conclusion by using p-test where p is 1. So since p is 1, it is divergent. So the function with the smaller values is divergent, then by direct comparison test, the improper integral with bigger function should also be divergent too, okay? So from 1 to infinity, the function with bigger values should also divergent. This is also divergent by using which test? Direct comparison test, okay? By direct comparison test. Okay, that's it. Tests are so useful when you use them efficiently. Okay, let's move on with the next example. Here, the question is still the same. Is it convergent or divergent? We don't want to compute the exact result. Again, we need to invent some inequalities to be able to use direct comparison test. Here, the most famous inequality about cosine and sine function is this one, right? Then we can add 2 to each side plus 2, okay? And it looks like that. And then to obtain the exact given function here, we can multiply everywhere with 1 over x, right? Let's do that. Let's multiply. Okay, let me emphasize what we are doing. We add 2, then we are multiplying 1 over x everywhere. So what we obtain is 1 over x is less than cosine x plus 2 over x is less than 3 over x. Again, we will use this inequality and look at the convergence divergence behavior of this function. Be careful, the integral is not from 1 to infinity, but pi to infinity. You should keep that boundaries, okay? Or you can fix that boundaries at the end. There are 2 ways to go here. Okay, since we will be using p-test in the next line and p-test has these certain boundaries, okay, let's keep it as from 1 to infinity. Okay, this is here p is 1, so it is divergent by p-test. Right, p is 1, divergent by p-test, then we should use direct comparison test to conclude that the function with the smaller values is already divergent, meaning that this function from 1 to infinity should diverge too. It is also divergent by direct comparison test. Now you need to fix the lower boundary from 1 to pi, right? If the integral with boundaries from 1 to infinity is divergent, then when you change the lower bound, which is 1 to pi, the result won't change. It will also be divergent. Also divergent because, let me explain that with a graph. Okay, you know, this function is between 1 to 3. I mean, the values of it is always positive. Let's say something like this. Let's draw a symbolic graph for it. So what we learned from this statement here is the integral of it from 1 to infinity, which corresponds to the shaded area. We understand that it is divergent. So the shaded area here is infinite. The result of the improper integral is infinite. What we are doing here is we are changing the lower bound, which is 1, with pi. Then we are taking the integral from pi to infinity. So we had an infinite shaded area there. We just subtract some finite portion of it. That's why this new shaded area will also be infinite, okay? Because what you are taking out, what you are canceling by changing 1 to pi is just a finite portion. So let me continue with the next example then. In this example, we will be using limit comparison tests. So let me remind this statement of it. Recall limit comparison test. To be able to apply limit comparison test, you need to choose some other function, okay? You need to choose it by yourself. I will explain how to choose it, okay, in the example. After choosing this function, then you will look at the limit of the ratio of these two functions, right? You will compute this limit by using your skills. You can apply anything you like. Let's say you compute the limit as L. Here, g of x is the chosen function, f of x is the function given in the example. So, depending on the result here, if the result is between 0 and infinite, if L is a finite number different than 0, then the conclusion is both converge or both diverge. Okay, we will be using this conclusion. So let's apply it. Here, f of x is this one, given in the question. 1 over e to the power x minus x. So by using the argument that we need to choose the dominating terms, you can determine your g of x function. So how to choose it? Choose the dominating terms. So nothing to do at the denominator, but for the denominator, this one is dominating much more bigger than x. Remember the graphs, e to the power x is always bigger than x, and x is always bigger than ln x. So this dominates the denominator. That's why I choose just that part. So g of x function is this one, e to the power x over 2. Now I will take the ratio of them, and maybe no need to write in this form, and take the limit. So now I am taking the ratio like this, f of x over g of x. As x goes to infinity, what do we have here inside the limit is this one, 1 over square root of e to the power x minus x, 1 over square root of e to the power x. So this is computing the limit of, let's write everything in a common square root. I can take e to the power x parentheses here. Okay, it's something like that. Now, if x, let me do the simplification first. These are simplified. When x goes to infinity, what happens to this part? Normally, it is infinity over infinity, you know. Limit x over e to the power x as x goes to infinity is an indeterminate form. But you can easily apply L'Hopital's rule here. Take the derivative of the numerator, which is 1, take the derivative of the denominator. Now send x to infinity, then denominator goes to infinity, so your result is 0. So this part goes to 0, then the limit becomes just 1. So the limit is as desired, right? It satisfies this condition here. Then we can use the conclusion. So what we obtain here for the limit is, it is a finite number between 0 and infinite, so use the conclusion. The functions f of x and g of x should both converge or diverge. Both converge or both diverge, then I need to understand the behavior of g of x function to conclude something about the behavior of f of x function. Okay, now, time to understand the divergence, convergence behavior of g function that you choose. We choose that function as this one. How to take this integral? 1 to infinity e to the power minus x over 2 dx. This is an improper integral, you know, where the problem is with the infinite intervals. So you handle it like this: limit as b goes to infinity. You will name this part as b e to the power like that. How to evaluate that integral? It's an easy integral. So let's do that. Limit b goes to infinity, evaluate the integral itself divided by the constant coefficient there, 1/2 minus 1/2, where x is from 1 to b, okay? And the next line then becomes b goes to infinity. I will insert now upper lower boundaries, okay? So you can write this down as minus 2 times e to the power x over 2. Okay, now insert b here, insert 1 here. Take the difference. Minus 2 over e to the power b over 2 minus minus plus 2 over e to the power 1/2. Then now time to send b to infinity. E to the power infinite is infinite, 2 over infinite is 0. This part goes to 0 in the limiting case. So the result is just this part, which is 2 over like that. So you can write it also like this. So improper integral of g of x function, after doing all those computations, we understand that its result is finite. This is a finite result. That's why we will call this improper integral as convergent now, as its result is finite. So this improper integral is convergent, meaning that we already applied limit comparison test here, right? And find the limit as 1, indicating that they either both converge or both diverge. Since g of x is a convergent improper integral, then f of x should also be convergent, okay? So let me write down the result. What we obtain is g of x dx, where the integral is like this, is convergent. Then by using limit comparison test, the original question, our example, which is given by this expression, is also convergent by the help of limit comparison test, okay? So that's how you should apply limit comparison test. It seems a bit long, but it's not. I wrote too much. You can write a summary of it. First of all, you need to choose some other function, g of x, to be used in the ratio of the limit. Compute the limit. Once you find the limit between 0 and infinity, you can use this conclusion. And of course, to be able to use that conclusion, you need to know the behavior of g of x function. According to its behavior, whether it's convergent or divergent, you will say the same thing about f of x dx. Okay, so let's move on. I think I can leave this as an exercise for you. Very similar one. So let's move on with this one, for example. Okay. So let me see what we can do for this. The question is determine whether it is convergent or divergent. Obviously, you need to invent some inequality consisting of your function. So let's compare this function with this one. Which one is bigger? Which one is smaller? So what kind of inequality should I put here? Look at the denominator here. The denominator is smaller, right? So you are dividing with a smaller denominator. So the expression got bigger. By the way, this is just like that. As x is a number between 2 and infinity, this is not absolute sign of x, but just directly x. Now we need to try to understand the improper integral of this function. As we always use, p here is 1. So it is divergent by using p-test. As you can see, the improper integral with the smaller values is divergent. Then what happens with the improper integrals of the function with bigger values? Of course, it will be divergent too. So then the improper integral of this function, which has bigger values, should also be divergent. Is also divergent by direct comparison test, okay? And let me also try, before I stop, let me also try this one. Let me first invent some space here. Okay. 57. By the way, you also need to fix this lower boundary. You know, it is from 1 to infinity, but as I explained above, you can easily cancel out some small portion because the result is already infinite. The result doesn't change if you take out some finite portion. Is also divergent, obviously, but what I did here is I changed 1 with 2. Okay, let me see. These two examples are also so similar. Here, you need to compare this function with some bigger or smaller function. Let me explain how to compare it. First of all, you can compare it like this. Sorry. You can compare it like that, as the denominator is bigger here. And then for this part, you can use p-test. Here, p is 2, right? And I guess if it is bigger than 1, so it is convergent. But yeah, this is a nice place that I can show you. If sometimes direct comparison test fails because the improper integral with the smaller values is convergent, you cannot comment on the function with the bigger values. If improper integral, if direct comparison fails, you can start thinking about limit comparison test. You can solve this question by using limit comparison test, and you need to choose some g of x for that. To choose g of x, you look at your f of x function, right? You choose the dominating terms. Dominating term for the nominator is this one. For the denominator is this one, obviously. So your g of x function should be x to the power 3/2, okay? Once you compute this limit of this ratio as x goes to infinity, you will find the limit as 1. and then they will both convergent or divergent, then you need to concentrate on the convergence divergence behavior of g of x. So it goes like this then. 1 over 3 over 2 here. P is 3 over 2, which is bigger than 1, so it is convergent by p-test. Since g of x is convergent, the original function should be convergent too, okay, by using limit comparison test. Okay, I wrote this part as a general, too quickly, like this great paper, but I put all the details. And I think that's enough for this week. Thank you for your attention.